Such a beast. I don't see one, so let's go with that.
Oh, long time no see. yeah, good to see you. Yeah.
Let's get started. We're very fortunate today to have Kareem El-Bady giving the colloquium. He's now an assistant professor and working backwards, I suppose, through his career before going to Caltech. He was a postdoc that mingled the Max-Planck Institute in Heidelberg, the Center for Astrophysics, and the Harvard Society for Rebels. An interesting case. He received his PhD in Berkeley and an undergrad degree from Yale. What he's going to tell us about today is how combing through Gaia data allows you to identify all kinds of marvelous new varieties of exotic stellar binaries. And because he can tell you about that, Margaret and I at the beginning.
All right. Hi, everyone. Thanks for the introduction. Thanks for coming. I'll just say before I start, I know a lot of you work on very different things, so please feel empowered to ask questions throughout the talk if something isn't clear. So today I'm going to tell you about astrometry, that is the measurement of small angles and small motions on the plane of the sky, and about binary stars. And both of these fields have a very long history, and their history is tightly commingled. So I'm going to start at the beginning with some history. So we'll start in 1779 with this guy, William Herschel. Herschel had a telescope with a 6-inch aperture, one of the best telescopes in the world at the time. And he liked to use it to observe and make drawings of all kinds of astronomical objects, including double stars. You can see one of his sketches here. And over the course of a few decades, Herschel observed several thousand double stars. So by double stars, we just mean pairs of stars that are close to each other in the sky. Here you can see modern images of some of the objects that he observed. And he not only, the goal was both to detect that a companion to a star exists, it wouldn't be resolved with the naked eye, and then also to measure the motion of the stars with respect to each other over the course of decades. And so he published several papers reporting these observations on the changes in the relative positions of the double stars. So the interesting thing is that Herschel was not looking for binary stars, which is the main topic of my talk. Actually, Herschel didn't know that binaries existed. He thought all stars were single. What he was trying to do was to measure stellar parallaxes, that is the apparent motion of a foreground star compared to a background star. So here's a little movie by Eric Tollerud that shows what he was trying to measure. Earth goes around the sun. If you have two stars close to each other, one is in the background and one is in the foreground, then you can measure the apparent motion of the foreground star with respect to the background star that should be stationary. So he did this for more than 20 years, from 1779 to 1803. Kept measuring stellar positions and reporting the results in a series of papers. It's a pretty clever result, it's a clever idea, but you might be able to guess if you think about it that this did not work. And the reason it didn't work is that almost all of these stars are actually physically bound binaries. That means the two stars are at the same distance, and you can't measure the parallax of one with respect to the other because they have the same parallax. So Herschel didn't measure any stellar parallaxes, but he did discover that a large fraction of all stars have gravitationally bound companions, in some cases even at separations of thousands or hundreds of thousands of AU. OK, now we're going to skip forward about 40 years to this guy, Friedrich Wilhelm Bessel. He's most famous for his functions, you can see there. But actually, although this is probably what you've heard of, the Bessel functions were only a small part of his career. He worked on them for basically one summer. Most of his career was spent doing astrometry at Königsberg Observatory. And he used this instrument here called a heliometer. A heliometer is designed to measure changes in the apparent angular size of the sun as the Earth goes around its slightly elliptical orbit to map out the orbit. But you can use it to measure any kinds of small angles on the sky. And Bessel also wanted to measure stellar parallaxes. So he decided to measure the parallax of a binary star, 61 Cygni, just pictured here. And he chose a binary because he could make measurements of both components. So you make two measurements for the price of one, and then average them out to get the parallax. But unlike Herschel, rather than trying to measure the apparent motion of one star with respect to its companion, he measured the motion of the binary compared to these two reference stars, which I've labeled A and B, that are farther away. And over the course of more than a year, every night that it was clear, he went to his observatory and made very careful measurements of the angular separation between the binary and both of these two reference stars. And you can see these are separations of hundreds of arcseconds, so relatively wide. Not only that, actually, every night he made 16 different measurements of the distance of both stars to both of the reference stars, because he understood that one of the main challenges for these kind of measurements is atmospheric twinkling because of turbulence in the atmosphere. And you could beat down that noise if you made lots of different measurements. Right? The unsteadiness of the atmosphere is the greatest obstacle. And so I observe sometimes, and it's always difficult to lose a night or two of sleep. But if I get too upset about it, I think about Bessel, who had to do this every night, observing the same star 16 times in a row, then doing the other star, and then doing that over the course of a year. And it's not so bad. So here's Bessel's data. I've plotted now the displacement in right ascension of the binary compared to one of his reference stars as a function of time. And I just plotted a sinusoid on top of it. And that sinusoid is the first stellar parallax. So Bessel measured a parallax of 0.31 arcseconds, which corresponds to a distance of 3.2 parsecs. And you can now see the modern measurement from Gaia, which I'll talk about in a minute. But you can see Bessel's measurement was actually very good. It's accurate to within 1.5 sigma or so, better than many of our reported uncertainties. So this was the first parallax, set kind of the scale of the solar neighborhood and how far apart the stars are. Everything was good. The other cool thing about this, because it is a wide binary, Bessel could actually measure the apparent motion of the two stars with respect to each other because of their orbital motion. And so he deduced that they were moving by about 2/3 of a degree per year. And from that, he inferred that the orbital period must be at least 540 years, right? Because it has to do 360 degrees per orbit. And we know the true orbit is something like 700 years, so that was also accurate. This wasn't a problem for the parallax measurements because the motion is much slower than the parallax, which is all within a year. Things got a little more confusing a few years later when Bessel tried to make these same kind of measurements for other stars. So here he's measuring the motion of the star Sirius, the brightest star in the sky. And you can see the last 20 years of data here is Bessel's measurements, and then he combined it with some other measurements from previous catalogs. So this is 50 years worth of data. It's long enough that you don't expect to see parallax on this axis because we're averaging, right, the parallax is just within a year. And you'll see the strange thing with Sirius is it's not moving in a straight line. Right, first moving in one direction, and then suddenly it turns around and moves in the other direction. And there's another star, Procyon, for which he made similar measurements and saw the same thing, no linear proper motions. And the challenge with these objects is that unlike in 61 Cygni, they don't appear to be double stars. So here's an image of the two stars. You can squint really hard and you won't see another star there. And so that was confusing. It looks like there's some source of gravity that's perturbing the orbits, but there's nothing there that could be responsible for it. And so if you read this paper, Bessel goes through lots of different possible explanations for what could be doing it. And eventually he arrives at what, in retrospect, is a very bold claim. He says, if we were to regard Sirius and Procyon as double stars, then it wouldn't be surprising for them to be accelerating, but you don't see a companion. And he says, well, the existence of numberless visible stars can prove nothing against the existence of numberless invisible ones. So he didn't say, well, probably there's just something wrong with the data, wrong coordinates, or somebody got confused about the reference system. But he says, no, there must be numberless invisible stars. So a bold claim, but it turns out in retrospect it was a smart claim to make. And the answer is that these are double stars, but their companions are very faint. So here now is an image with HST of Sirius. You see Sirius A is the bright star in the middle, but off in the lower left, about 1 million times fainter than Sirius, you see Sirius B. And Sirius B is a white dwarf. So it's a star that was initially more massive than Sirius itself, but it has terminated its evolution, stopped fusing, and now it's just this faint, cooling ball of carbon and oxygen. And you can see now here also with HST, astrometric orbit of Sirius A about Sirius B. You can see now here the uncertainties are about 3 milliarcseconds. So that's going to set the stage for most of the rest of the talk. We can now make these kind of measurements on large scale with the Gaia mission. So if you're not so familiar with it, Gaia for 11 years sat at L2 and scanned the sky continuously, making astrometric measurements. So it orbited around its axis with a period of 6 hours, scanning out an annulus, but then it precessed with a period of 63 days. And so as a result, roughly once a month, Gaia will come back to each position on the sky, measure where all the stars are with respect to a distant static background. And the amazing thing about Gaia is that it can make these measurements with a precision at the bright end of 0.01 milliarcseconds, which is a very small angle. Just for some reference on how small of an angle 0.01 milliarcseconds is, if I sit with my telescope in California and point it at Maryland, 0.01 arcseconds is the size of a human hair projected in Maryland. And this is how precisely Gaia can measure the positions of stars. Some people find this impressive, but astronomers are used to very large numbers and very small numbers. So you might be like, human hair. Maybe a potentially more impressive comparison is this image. So I think of this as one of the highest resolution images in astronomy. This is the Event Horizon Telescope image of the black hole at the center of M87. And this image is 0.1 milliarcseconds on a side. Right? So the precision with which Gaia is measuring stellar positions is 10 times smaller than this image. That doesn't mean that Gaia has the resolution to make this image. It doesn't. But it can centroid a star to an error bar of 1/10 the size of this image. Another reference point is that Bessel could make astrometric measurements with a precision of order a fraction of an arcsecond. And so Gaia can do about 10 to the 4 times better than Bessel did. And so Bessel can measure parallaxes and orbits for binaries that were a few parsecs away. That means Gaia can do this at a few tens of kiloparsecs if the star is bright enough. A few tens of kiloparsecs is basically the scale of the Milky Way. So if you have a bright star, Gaia can do astrometry for it and detect its orbital motion all throughout the Milky Way. So what does the data actually look like? Well, here's some real epoch astrometry from Gaia as of DR3. So in the first 3 years, Gaia looked at this star something like 30 times. Each time measured its position. We've now taken out the parallax and the proper motion, and you see it's an ellipse. And so the properties of that ellipse will tell us about the properties of the companion. So sadly, Gaia stopped taking data earlier this year in February after getting data for 11 years. That means by the end of the mission, Gaia looked at each point in the sky about 120 times on average. 120 is much more than the number of free parameters in an astrometric orbit. So if you have a binary with a period of less than something like 20 years, there's a good chance Gaia will be able to fit its orbit. But only the first 3 years of this 11 years of data have actually been fully processed and published. So the next data release is coming next year. I'll talk about that more. And the last data release will be some years after that. And it turns out for astrometry, a long time baseline makes all the difference. And so the best results from Gaia are still to come in the future data releases. OK, so most of what I'll talk about is results from Gaia DR3, which came out in 2022, and we've been analyzing ever since. So what's plotted here on the left panel is a histogram of orbital periods of binaries published in DR3. Just in blue, I'm comparing them to the best astrometric mission we had before Gaia, which was Hipparcos. So Hipparcos fit orbits to 235 binaries, whereas with Gaia we had about 170,000. So it's a huge increase in sample size. And even if you don't only consider astrometric missions, but you consider all radial velocity orbits from other work, it's about a factor of 50 increase in just the sheer number of binaries for which we had orbits, which means that if you're looking for rare objects, it's a good place to look. What's plotted on the right here is just the color magnitude diagram of binaries with astrometric orbits. I mark where the sun is. These are mostly solar type stars within about half a solar mass to 2 solar masses or so. And that's set by a trade-off between the fact that more massive stars are brighter, but there aren't very many of them. Lower mass stars are fainter, but there are a lot of them. And so the Gaia sensitivity is best for stars around a solar mass. Also some red giants. So in my group, we're mostly interested in binaries where we think one of the components is a compact object. So it's gone through its evolution. There's been some interaction between the progenitor of the compact object and the star. And so I'll talk about each of these classes. But from the astrometrically selected candidates that we've had since 2022, we have something like 5,000 candidates where we have a solar type star and a white dwarf. Same idea as Sirius. Something like 50 where you have a solar type star and a neutron star, and around 5 where you have a solar type star and a black hole. These are candidates based on the astrometric orbit. And it turns out, although astrometry from Gaia is very good, it can go wrong in various ways. And so an important part of the follow-up is to get radial velocities to refine and vet these orbits. So we've been doing that over the last few years. Turns out most of these stars are fairly bright. They're typically 13th to 16th magnitude, and so we can get radial velocities with small telescopes. And so we have this campaign using these 3 telescopes here. They all have high-resolution spectrographs and can measure moderately precise radial velocities for tens of objects per night. And so here's an example of how this works. Here we have an astrometric orbit that makes a prediction for how the radial velocity of the star should be changing as a function of time. You see in this case it predicts it should be varying a lot. And then we go to the telescope, measure some radial velocities, and plot them on top. And sometimes it doesn't look so good. So this is a case where the star is apparently not moving at all, at least not on these time scales. And the radial velocities tell us there must be something wrong with the astrometric solution. I'll talk more about what causes these kind of problems in a bit. And it turns out we think it's mostly marginally resolved double stars where Gaia can't centroid them right, and that messes up the astrometric orbits. But the main takeaway here is we have to do radial velocity follow-up if we look for rare objects in order to make sure that we don't have spurious solutions. Here's another case. Here we have a prediction for how the radial velocity should be changing, but it's got a fair amount of scatter. And that's just because the Gaia orbital solution has some uncertainty in the period. When you predict into the future, that leads to a uncertainty in the phase. And so prediction is it could be sitting on any one of these lines. Then we go measure a few radial velocities. I'll plot them on top. And in this case, it does look like they're moving in the right direction, but it's hard to see, is there any one curve that goes through all of them. But I can now take the radial velocities in the astrometry and fit them together. And then I can get a tight constraint on the orbit, which is not something I could get with 3 radial velocities if I didn't have the astrometric orbit. So in my group, we've been following up all these different compact object binary candidates over the last few years. And so I'll tell you some of the highlights now from each of the classes. So the first object we found called Gaia BH1. This is a solar type star. You can see there where it is on the color magnitude diagram. Roughly solar metallicity, mass and luminosity similar to the sun. If we look at just the astrometry, the Gaia astrometric solution tells us that the star is going in an ellipse like this with eccentricity of around 0.4 and a period around half a year. and the distance is about half a kiloparsec. And then we did radial velocity follow-up. In this case, you can see the radial velocities are fully consistent with the prediction of the astrometric solution. And so when we fit the radial velocities in astrometry together, we get a 3D orbit for this star. If we then know its mass, or we say we know its net mass from its position on the color magnitude diagram, then we get a constraint on the mass of the unseen companion, which is 9.3 solar masses here. So we have a 0.93 solar mass star orbiting a 9 solar mass companion, but we don't see any light from the companion, and we take spectra and search for any faint signatures. There's nothing there. And so we conclude the companion must be a black hole, because if there were a 9 solar mass star or some combination of stars adding up to 9 solar masses, we would see the light. So we've got a system like this, a black hole and a star separated by about 1.5 AU. And the question is, how do you form this? And we say, well, black holes form from massive stars, as far as we know. So let's put a massive star there. To make a black hole around 9 or 10 solar masses, stellar models tell us you need a progenitor somewhere around 40 solar masses at solar metallicity, although it's fairly uncertain. So let's say we start like this, and then we let stellar evolution proceed. The difficulty is that the 40 solar mass star at the end of its life will expand and become a red supergiant. And red supergiants of this mass have maximum radii of around 10 AU. So they're too small to fit in the current orbit without running into this star. So this is generically a challenge for forming black holes orbited by stars if the separation is less than about 10 AU. And one solution that's been proposed is what's called a common envelope episode, or common envelope evolution. And the idea is your star starts somewhere out in the outer envelope, right? Maybe the star was born out here. Then the progenitor of the black hole expands, runs into the star, and the star will spiral in through its envelope. As it does that, it'll release some orbital energy because it's falling into the potential. And if you're lucky, if the star is lucky, that orbital energy will be enough to eject the envelope of the red supergiant on top of it, and then you'd be left with a closed binary. I say if you're lucky because it's going to be pretty hard for this star to eject something like 20 solar masses worth of envelope. It's only a 1 solar mass star, but it's not totally out of the question. But the main challenge for that kind of evolution is that you can only eject the envelope of the red supergiant if you spiral all the way in, so you're close to the core of the red supergiant. Because you only get a lot of orbital energy to eject the envelope once you get deep into the potential, right? The potential goes as 1 over r. And so all these post-common envelope models would predict you should have a star and a black hole close to each other. But the challenge is the system we find with Gaia, the separation is still 1.5 AU. So it's like the star came in a little bit, but then stalled if it formed through this kind of channel. OK, that was Gaia BH1. We found another one fairly similarly, Gaia BH2. Here we again have a star around 1 solar mass and around solar metallicity. But in this case, the star started to go up the giant branch. So it's on the lower giant branch. Both of these have thin disk-like orbits in the Milky Way. And this one has an even longer period of something like 3.5 years, so a separation of about 5 AU. So it's still wide enough that we think we can't fit the progenitor of the black hole in the orbit, but too wide to be the outcome of common envelope evolution, we think. And it seemed for a couple of years like that was it. We searched all the DR3 orbits. We didn't find any more black holes. But then last year, we were excited. There's a third black hole published based on Gaia data. This one is not based on DR3, which has already happened. But this is an object that was discovered in preparation of the data for DR4, which will be published next year. But it was sufficiently exciting that it was published early. And so what's exciting about this object is it's a 33 solar mass black hole, which is more massive than any of the black holes we know about in X-ray binaries or any other kind of system in the Milky Way. It's a very long period, about 11 years, which is why it didn't receive an orbital solution in DR3, because DR3 was based on only a few years worth of data, but it could get a solution in DR4. The other thing that's unusual about this object is the metallicity. It's minus 2.5, which is quite metal poor. If you grab a random star in the solar neighborhood, you have to grab 10 to the 4 of them before you find one as metal poor as this one. And so we think these two peculiarities, low metallicity and high mass black hole, are probably not unrelated. So that I think is one of the cool things about these kind of black holes we can find with Gaia, is that we have metallicities and compositions of the companion stars. So here I just show a portion of the spectrum of Gaia BH1 at solar metallicity, BH3 at metallicity minus 2.5. You see the lines are much narrower and weaker at low metallicity. And we think that the star and the black hole in these systems form together, right? It turns out that it doesn't even matter whether these are primordial binaries that actually form as a binary or whether they form in a cluster and pair up later. In any case, the composition of this star should be the same as the composition of the cloud of gas that the black hole formed out of. And so by measuring the metallicity of the star, we can measure the metallicity of the progenitor of the black hole, which is something we can only do for these kind of systems, right? Like with gravitational waves, we will eventually have thousands or tens of thousands of black holes, but we'll never know the metallicities of any of them. Whereas here we just have a small number, but we do have metallicities. And so I mentioned 3 black holes from Gaia. You have 2 at around solar metallicity and a mass of around 10 solar masses, 1 at low metallicity and 30 solar masses. I'm an astronomer, I know what to do. Whereas it looks like we have some correlation here, although it would be nice to have a couple more data points to put on the plot. There is a natural stellar evolution reason you might expect this kind of correlation to exist, which is that at low metallicity, massive stars have weaker winds, or are predicted to have weaker winds than at solar metallicity. And so they don't lose as much of their envelopes during their pre-end stage evolution, and therefore can leave behind more massive black holes. So this is something that's been predicted for many years based on evolutionary models, but something we couldn't test until now because we just don't have any massive stars with metallicities anywhere near this low in the local universe that we can study. Okay, so I mentioned it seems difficult to form these kind of systems through isolated binary evolution in a common envelope. An alternative possibility is that they form through dynamical evolution in a cluster, a dense environment where you have lots of stars. And here maybe you can form the black hole first by itself, and only later on in its evolution do you pair it up with the companion star. So there have been several papers with different models for how these systems may have formed. These papers have shown that you definitely can make binaries dynamically that have periods and masses and things like that comparable to the observed systems. But the story is usually pretty complicated. And so if you look closely at these, it turns out most of these channels still include a common envelope between a massive star and a low mass star. But these common envelopes are a bit easier to survive because the star that's undergoing the common envelope is actually a merger product itself, so it has a different core envelope structure. And so I would say there are several plausible models here that could work, but there are a lot of uncertainties as well. So it still remains to be seen if this is the main formation channel. That being said, there is one good piece of evidence that this dynamical formation channel does happen in nature, which is that this most massive black hole, Gaia BH3, is in a stellar stream. So there's something like 20 other stars that have the same 3D orbit as this star and sit on an isochrone with the same composition, same abundances. And so it seems like this star used to be in a cluster. That cluster is now started to be tidally disrupted, but they're still moving coherently through the galaxy. And if that's true, then the progenitor of this binary would have had no choice but to interact with other stars in the cluster when the cluster was still bound. So I'd say this object is pretty good evidence that at least some of these black holes or binaries are forming dynamically. So here's our census of black holes in the Milky Way. The systems I've talked about with Gaia are over here. Right? These are these widely detached black hole star binaries. Over here, systems I haven't talked about, but these are X-ray binaries, where you have black hole that's accreting from a stellar companion, and we detect them because they're bright in X-rays. And then there are also a couple systems in between discovered by radial velocity surveys. And the y-axis here is distance. And so we think we're not at a special place in the universe or a special place in the galaxy, so distance is kind of a proxy for how common something is. And based on this plot, we think these kind of wide binaries with black holes that we're detecting with Gaia are significantly more common than the close binaries we detect with X-rays, right? Because all three of the closest known black holes we know of now are these wide systems from Gaia. And if you took these systems from Gaia and put them at larger distances like the X-ray binaries, you wouldn't be able to detect them because the angular size of the orbit would be too small for Gaia to resolve. But if you brought the X-ray binaries closer, you would still see them as bright X-ray sources. And I'll just mention there's one system over here. This is the only isolated black hole we know of. This is discovered by microlensing. And we think probably these things are even more common than these wide binary black holes, but at least with existing instrumentation, they're harder to find. I'll talk about that a little bit more also. So that was the black holes, but we're also following objects that look similar astrometrically, but just have somewhat lower dynamically implied masses. And there are 21 of these where after we got the radial velocities, we can confirm the Gaia orbit, and we find a companion mass high enough that we think it's most likely a neutron star. That means more than about 1.3 solar masses. Here I'm just showing the constraints on their radial velocities. On the left, it's the radial velocities plotted on top of the astrometric prediction. And on the right, I'm fitting the radial velocities and astrometry together. But you can see in all cases, the radial velocities are consistent with the astrometry. You can also see the orbits are not circular based on the fact that these radial velocity curves don't look like sinusoids. And here's a little movie showing the orbits of some of these systems. So here the yellow star traces what Gaia actually sees. And each time there's a red dot, that's an astrometric measurement made by Gaia before DR3. And then the little blue point that we don't actually see, but we can infer what it must be doing based on Kepler's laws. And so you can see these systems, we're showing 3 years of data here. So they have periods ranging from about half a year to 3 years, separations of order in AU, and moderately eccentric. They're qualitatively pretty similar to the black holes. And they are difficult to form for the same reasons as the black holes, right? You first of all have to survive the common envelope. In addition, we think neutron stars are often born with a natal kick. So during the supernova, the neutron star recoils in some direction. And the fact that these binaries, despite being wide, stay bound, tells us that that kick can't have been very strong. Yep?
These are the plane of the sky, or
These are observed as, they're plotted as observed in the plane of the sky, yeah.
The uncertainties on those red points, they're really the size.
They're smaller than the points. Yeah. So here's the mass distribution of all the neutron stars and black holes we found with Gaia. You see there's a big peak around 1 to 2 solar masses. Here's a zoom in on that peak, which does have some structure. And there are a couple objects around 9 solar masses and one way off the charts. But we don't have anything in between so far. And it's not because we're not sensitive to them, in the sense that it's easier for Gaia to find a 5 solar mass black hole than it is for it to find a neutron star, right? The sensitivity basically just depends on the size of the orbit, which depends on mass. So we can certainly rule out a scenario where there are more of these objects than there are these. That said, we are more sensitive to 10 solar mass objects than to 5 solar mass objects. So we're still dealing with small number statistics, but we can at least rule out a mass distribution that's just a draw from the IMF and being passed through a monotonic initial final mass relation. Here's now the same data, but now in the context of other kinds of neutron stars and black holes known. So the Gaia systems are over here. These are neutron stars and radio pulsars, and then these are the X-ray binaries. And you can see over something like a factor of 10 to the 4 in orbital period for all these different kinds of binaries, we've got this bimodality in masses. That's not to say that there's nothing in between. There are a few objects like this one, and there are a few other candidates, these guys, that seem to straddle the gap. But there's at least a bimodality that it's less likely to have a compact object with mass down here than up here or down here. And so we think probably that tells us something about or at least that it may tell us something about the supernova mechanism, that stars either accrete a lot of their envelopes when they collapse or successfully explode and don't accrete anything. But it's complicated to interpret because we're only seeing the black holes that have survived in binaries, which are not necessarily a representative sample of all black holes. So you could imagine that these lower mass black holes might be less likely to survive in binaries. Either they merge or they're born with stronger kicks, in which case you could also explain this data that way, with even while there are a lot of isolated low mass black holes. Okay, and then last of all, I want to talk about the white dwarfs. So the white dwarfs, we have many more than neutron stars. Before I get into the data, I'm going to show a prediction from a binary evolution model of what you might expect. So here I've run a binary evolution model using this code Cosmic, which you may have heard of. It's a pretty vanilla binary evolution. I simulate a galaxy full of binaries. I run it for 10 gigayears, assuming a constant star formation history. At the end, I take everything that has a main sequence star and a white dwarf, and then I plot the orbital periods and the masses. You see there's a lot of structure here. I won't go into a lot of detail, but there's a story for why this diagram looks like it does. You have low mass white dwarfs formed by stable mass transfer at short periods, higher mass white dwarfs that went through Kama envelope. Systems out here didn't interact except through winds. And then there's this region of around 100 to 1,000 days where there shouldn't be many white dwarf main sequence binaries because those are systems that get cleared out by Kama envelope, right? The progenitor of the white dwarf runs into the companion. So now I'm going to take the systems we have from Gaia and plot them on the same axes. And it turns out that this model isn't doing so well. So basically 100% of the white dwarfs we find with Gaia are in the region where the model predicts there shouldn't be anything. It's not 100% fair in the sense that we do know of white dwarfs that live over here. Gaia is just not sensitive to those, right? Because Gaia needs the orbit to be large enough that it can resolve the astrometric motion. But nevertheless, Gaia is telling us there are a lot of white dwarfs with these periods when the model predicts there shouldn't be any. So my student Natsuko Yamaguchi has been working on these. The first thing she did is get follow-up radial velocities to confirm whether these orbits are accurate. The short answer is that the vast majority of them are. Here's a plot showing the masses of the white dwarfs and the separation at periastron, which is a function of orbital period, for the Gaia white dwarfs, where she's done radial velocity follow-up, compared to other samples of white dwarf main sequence binaries known before Gaia. So these are called post-common envelope binaries. They've been studied a lot with SDSS and other surveys. So basically almost all the systems we had before Gaia were down here with periods of around a day or less, whereas all the systems we find with Gaia are up here at periods of more than several months. And we can do population modeling now to understand how common these are. And I won't go through the details, but the short answer is that we think these are actually much more common than these. They're just harder to find if you don't have astrometry, because with radial velocities or light curves, you're much more sensitive to short periods. And so we don't fully understand how these form. We have some models where maybe mass transfer can be stable on the AGB. But the short answer is that the challenge of forming these is not that different, I think, from the challenge of forming a black hole or a neutron star in the same kind of orbit. So the fact that many of these exist may suggest that there's just something wrong with the Kama envelope models that can also explain the black hole and neutron star systems. So the last thing I want to talk about is the selection function. And the short introduction to this is we find all these cool objects with Gaia, but in order to do science with them and compare models to data, for most of the questions you'd like to ask, you have to know the selection function. That is, what objects that are predicted by the model will you be able to detect, and which ones will you not be able to detect? Otherwise, you can do studies of individual objects, but in order to do anything with population, you have to know both what you see and what you don't see. And so this is because Gaia is a complicated mission, there were a few years where I think nobody tried to model the selection function. But I'm going to argue that it's actually tractable, although it's complex. So why is it complex? This is a plot from the astrometric binary processing paper in DR3. One of the complexities is that a bunch of different astrometric models are fit sequentially, and the simplest one that gives an okay fit to the data is accepted. So it could be that you get a good fit with a more complex model, but that complex model never gets tried because the simpler one is accepted first. Another complexity is that after an orbital solution is fit, it turns out there's various varieties of bad solutions that are just not correct, that have to do with period aliasing and marginally resolved binaries. And so they show up in these parts of these diagrams. And in order to filter those out, the Gaia collaboration used these empirical cuts where they drew lines in things like eccentricity error, parallax errors, and major axis error, and they reject solutions on one side of the line. So the goal is to make a clean sample, but of course in the process you lose some objects that would have had good solutions. So you have to model these kind of cuts. You have to be able to predict, say, what is the eccentricity error going to be in order to know whether your binaries should get an orbital solution or not. Even so, Gaia observations should be easy to simulate. The reason they should be easy to simulate is, Gaia is a very well-controlled mission. We know at any given point where it was looking. Or at each point in the sky, we know when Gaia looked at it. We have a good empirical noise model. That is, for an object of a given brightness, we can say what the uncertainties in the individual epoch measurements should be. And so what I've done is try to build a kind of end-to-end pipeline to simulate Gaia astrometry at the epoch level. Okay, so the way this works, let's see. I'll start with a simulated Milky Way-like galaxy full of binaries. I observe each one according to the Gaia scanning law. I predict mock astrometry that looks like this based on an empirical noise model. And then I fit the same cascade of astrometric orbits that was fit to the real DR3 data. And when I do that, I get plots that look like this. So this is now simulated data, but you'll see it has very similar structure to the plot I showed a second ago with real data, if I just click back and forth. And so in the simulation, we know what these bad solutions are, where they're coming from. And we can then apply the same cascade of quality cuts. And the end result is this. So here I now take only the orbits that make it through every step of the cascade from this mock catalog. And I compare that, which is in pink, to the real catalog in blue. And you see they agree reasonably well. They're not perfect because probably we don't have exactly the right underlying binary population in the model, and there could be some complexities we're missing. But the fact that the shape agrees pretty well suggests that we understand the most important parts of the selection function. And so we're then in a position to ask, if I had a binary with some properties, will it eventually get an orbital solution in DR3 or not? And so the takeaway from this is Gaia is not complete anywhere, right? There's no region of period or mass or distance where it's complete. But if we understand the completeness well enough, that's enough for most of our applications, because we can just take our simulated population and pass it through that completeness and then compare that, the post-completeness function prediction to data. So we've used this completeness model, which by the way is public, you can use it too, for a few different applications so far. One I'll talk about here is from my student Pranav Nagarajan, where he took these two different models of how these Gaia black holes that we're finding are forming. One says forming through isolated binary evolution, and the other one says it's dynamical assembly in clusters. So both of these models are coupled to a simulated Milky Way-like galaxy. They predict a Monte Carlo population of black hole binaries all throughout the galaxy. We can then simulate what those binaries look like when Gaia observes them, pass them through the whole selection function, and at the end you get a mock catalog of black hole binaries that would be observable from both of these models. And so here's the end result. The isolated binary evolution model predicts 0 detectable black holes in DR3. The dynamical model predicts, I think, 17 plus or minus 4. The 0 is really 0 plus or minus 0, meaning that even if you put the sun at lots of different places in the galaxy, you pretty much never get a detectable one. And then observed in DR3, we have 2, because the third one was based on DR4 data. So I won't say we've solved the problem yet, but we've at least bracketed the observations in terms of models that can predict the formation of these objects. And so probably if they're forming through isolated binary evolution, these models are missing an important ingredient. If they're forming dynamically, these models are overestimating either the occurrence rate of the kind of clusters that they form in, or the binary fraction within those clusters, or some of those details. We can apply the same model to the white dwarf binaries. So here's the observed period distribution of the white dwarf main sequence binaries. You can see it has quite a bit of structure. But it turns out most of that structure is driven by the selection function. So for example, it's hard to find a binary astrometrically that has a period of a year, because the parallax motion will be totally degenerate with the orbital motion. So if we use a selection function, we can correct this for the incompleteness. And what comes out here is the observed data basically divided by the marginalized selection function for that sample. And you get something that's actually pretty flat. So maybe it's increasing a little bit towards close separations. But there's really no hint of a valley cleared out by common envelope, which is what any binary evolution model would predict. Just for context, the classical post-common envelope binaries that we knew about before Gaia and the things that become cataclysmic variables, they're all at even shorter periods, basically less than 10 days, and Gaia astrometrically can't say anything about those. So there's still a little region connecting these that we have to access with things besides astrometry, like radial velocities. OK. One more thing I want to talk about is new light on an old black hole from Gaia. So this is an image of the black hole V44 Cygni. It's an optical image with an X-ray image on top of it. And so in the X-rays, you see this echo from an outburst that the black hole had. V44 Cygni is kind of one of the best studied black hole X-ray binaries. And so with Kevin Burge, I was looking at this black hole. We were thinking of studying it with Kevin actually was thinking of studying it with high resolution imaging, and he just wanted to look at the field of sky in the optical image to orient himself of what to observe. And so you zoom in, you see there's V44 Cygni. You zoom in a little more, and the kind of obvious thing in this image, if you look at it, is that there is 2 stars right next to each other. One of them is V44 Cygni, and the other one, all the papers in the last several decades, that is an interloper star that just happens to be next to V44 Cygni and makes it hard to observe. But the interesting thing with Gaia is we can measure proper motions and distances for these, and we can imagine we're Herschel at the beginning, looking for wide binaries. And we put on the proper motions, and it turns out these 2 stars have exactly the same proper motion. And then we did radial velocities. They also have exactly the same radial velocities. And so from those 2 things, you can calculate what's the probability that just by chance 2 unrelated stars would have such similar proper motions and velocities, and it's about 10 to the minus 7. So it seems like this is a gravitationally bound pair. But of course, the inner binary that's unresolved here, or the black hole that's unresolved here, is also a binary. So here's what it looks like schematically. You've got a black hole that's in the process of devouring a companion star that's very close in. And then about 5,000 AU away, you have another star that's orbiting the both of them. And the orbital velocity of that distant star is quite small. It's only a couple of kilometers a second. So we can learn a few things from this system right away. One of them is that this black hole must have formed with a small kick. Right? That's one of the uncertainties about black hole formation. We think sometimes the black hole recoils during its birth. But in this case, it can't have been born with any significant kick because it would have lost this star over here that's only bound by a few kilometers a second. Another thing we can learn is that maybe the third star doesn't just happen to be there, but it actually played an important role in the formation of the inner binary. So my student Cheyenne has worked on models for how this could happen. Schematically, the way this works, you start with an inner binary, something like 100 AU. Third star is still far away. At 100 AU, you don't have to worry about the common envelope because the progenitor of the black hole will go through its evolution, form a black hole, no problem. So you get a black hole and a star still about 100 AU away. But then eventually the third star will start to perturb the inner binary. And if the mutual inclination is correct, the third star can drive the inner binary to very high eccentricities, what are called Kozai leadoff oscillations, to such high eccentricities that at periastron, tides can actually remove energy from the orbit, and the inner binary can dramatically shrink, giving rise to the mass transferring system that's observed today. And so it turns out this V44 Cygni is one of the closest black hole X-ray binaries, and one of the few where if there's a tertiary, you'd actually be able to detect it. So the fact that we found a tertiary to one of them makes us think that these tertiaries are probably important in forming other ones as well. We just can't always detect them. And I'll just mention, Cheyenne has applied basically the same models to cataclysmic variables, where you have the same picture, except instead of a black hole, you have a white dwarf. And we also find dozens of those that have resolved tertiaries that are co-moving with them. So probably these tertiaries are important for making mass transferring compact object binaries without a common envelope in lots of different scenarios. Okay, what's next? Well, I mentioned at the beginning, next year in December, we'll have Gaia DR4. A few years after that, we'll have DR5. The most important difference in DR4 is you have twice as long an observing baseline. But a longer observing baseline means you're sensitive to longer orbital periods. And binaries with longer orbital periods are bigger. So you can see them farther away. And so here's a simulation based on this selection function tool I was talking about earlier, predicting the observable population DR3, DR4, and DR5. And you can see you get a dramatic increase in search volume with each data release. And that's why, even though we have to wait years between Gaia data releases, we should keep pushing at it, because for binaries, really, the longer the observing baseline, the larger sample we can find. And in particular, for black holes, we predict we'll be able to find about 30 of them in the same kind of orbits in DR4. What's plotted here is predictions from a bunch of different papers on how many black holes Gaia would find. You can see we started out extremely optimistically, got more and more pessimistic, and went way down in DR3, but we're just about to turn around and start increasing. Okay, I'll end there. Now is a great time to look at stellar mass black holes with astrometric and spectroscopic surveys. Gaia is just getting warmed up. Get excited for the next data release, December 2026. And binaries are key to most of the open and interesting problems in stellar physics. Thanks.
Well, thank you for talking a diverse range of interesting subjects. And Joe?
Yeah, that was fascinating. So the tertiaries shown at the end, you mentioned mass transfer, but what about Lidov-Kozai resonances? Can you test for that?
Yeah, I went through that quickly, but that's the story. The tertiary is too far away to have mass transfer, but the tertiary is what brings the inner binary together in the first place. So the tertiary makes the inner binary very eccentric. We don't actually see it at this phase because this happens very quickly. Then the inner binary shrinks, and by the time the inner binary gets to its final state today, there Kozai won't do anything because tides are dominating the inner orbit, but we think Kozai was important to get there.
Hey, thanks for this wide-ranging, fascinating talk. I'm curious about the population studies thing. So, I think what you're doing to do the forward modeling is all you can do that you have right now. But the other way to make the selection function simpler is to make the pipeline dumber. Select everything essentially. Is that going to be possible in future DRs, or is that Or is there some intrinsic problem with the pipeline or the data that makes it impossible?
So it will be better in future data releases. The choice in DR3 to fit this cascade of models was made in like 1990 when the mission was being designed, and it wasn't clear that they would even have enough computational power. In DR4, all the different models will get fit to each system, so you'll have a likelihood of each model, basically. And the other big thing in DR4 is the actual epoch astrometry will be public. So if you're not happy with the mission-produced catalog, you can make your own catalog by fitting the data yourself. So I think it will definitely enable more population modeling.
More questions?
Yeah, so Gaia's done now. Why don't
in the same direction.
No. All right. See, we're a binary.
Yes.
Why is there such a gap to DR5? Why don't you go right to DR5 now?
So I would love that. It's a little bit, so Gaia is a large collaboration. It involves more than 100 people and different units, each one producing one part of the data. And so I think for my own science, the epoch astrometry is most interesting. But the timeline of the data releases is basically set by the slowest moving part. And so in order, like the epoch astrometry for DR4 is done. It's been done for the last couple of years. But there's lots of other things like, calibrating the low resolution spectra and the medium resolution spectra and radial velocities, and measuring stellar parameters and things like that that aren't done. Then the timeline for these data releases was set a long time ago. I would be delighted if it was possible to push them forward a little bit, or even to have an early data release where just some of the data for DR5 that's already ready could be public earlier. I'm not sure if it's possible, but I've certainly advocated for it.
Thank you.
Okay, we'll go from Mark A to Mark B.
So, I was wondering, Gaia has those two telescopes that are about 60 degrees apart. Can you do relative astrometry between stars separated by 60 degrees?
Between stars separated by 60 degrees.
Or is it just two different telescopes where you do relative astrometry?
Right. I'm actually not sure off the top of my head. I think at the end, the astrometric solution is global at the end, like it's fit all of the stars at the same time, based on, all of the observations that went into the data release. But I do know, that the concept of two telescopes separated by 60 degrees was carefully chosen, and it wouldn't be possible to have as good of a solution with a different setup. Yeah.
Very nice talk, thank you. So, I have two questions. So, you showed the metallicity of the higher one, for metallicity. So there are several X-ray detectors. The metallicities of those should be detectable, right?
Yeah, that's right. I had a version of the plot with those on it. I didn't show it. Basically, the challenge is that, so first of all, almost all the X-ray binaries we know of are solar metallicity within like 0.2 dex. And the stars are rotating really fast, which makes it harder to measure the metallicities, and they're very faint, which makes it also harder. But basically, the answer from those seems to be that there's more scatter in the relation than my line predicts. So there are black holes in X-ray binaries that have best fit masses between something like 7 and 20 solar masses that are all at solar metallicity. So I think metallicity is an important factor, but it's not the only factor.
So the other question was that you had the black holes, you needed the radial velocity, but you don't do that for the neutron star and white dwarfs.
Oh no, we did do the radial velocities also. I kind of skipped over it, but let's see. Here's all the radial velocities for neutron stars. It's something like, it doesn't look like, it's only one slide, but it's like 100 nights of observing that go into it. Yeah.
Yeah, when you were showing the pipeline flow chart, one of them said orbit. Is the template by orbit just an unchanging two-body problem, I suppose? If if so, I'm just wondering if it's interesting to look for if you're missing anything from evolving orbits, like for example, from a closed triple or things like this. I mean, I know binaries are first, but you brought up triples already. So.
Yeah. So in DR3, it's just a Kepler two-body problem. In DR4, it will still be just a Kepler two-body problem is like the default that goes into the pipeline. But people will and should fit more complicated orbits. The challenge is just there's more flexible orbits always give better fit, so you have to decide how much better. I think the case where more complex models are most relevant is for planets, because for binaries and black holes and whatever, you always have a hierarchy. But for low mass companions, you can have several planets that are all at periods not that different from each other. So there will certainly be cases where either you have multiple companions or you have precession and things like that.
Yeah. So in the slide where you showed the overprediction from the dynamical pathway, what do you think in the models? Do you think it's an issue in the assumptions in the models that are leading to the overprediction?
I think so, in that if everything were accurate in the model, we would find these, and we followed up all plausible candidates. But there's a lot of different ingredients to the model. Like the ingredients to the model are what is the mass spectrum of clusters, or like what fraction of stars are born in clusters to begin with. How long do the
What is that assumption? What is the input for that? I'm curious.
For what fraction are born in clusters? I think it's 10% in this paper. And I mean you can't simulate the galaxy, all the clusters in the galaxy, right? So what they actually do is they simulate like 10 clusters with different masses, and then they make copies of them and move them around. And then other things are like, what is the initial binary properties in the cluster? What is the initial binary fraction, period distribution? And then also, what is the binary evolution that you put in? Because even though there's dynamical exchanges, there's also still common envelopes happening and mass transfer. And in the paper, we go into what happens if you vary some of those assumptions. And you can bring this down to 0, or you can blow it up.
Okay, one more question?
It was just a nice question. Like I thought, like, so the kick velocity is like inversely proportional to the mass. Like smaller black holes should get bigger kicks. But then, like the neutron stars, you see a lot, and you see like this 10 solar mass. So in between, you don't see them. So is it like neutron stars have more symmetric explosions, and that's why they don't get like disrupted? Or?
Yeah, I think it's a little bit. Let's see, where's the slide? It's a little bit uncertain. Definitely a lot of neutron stars are born with big kicks because we observe lots of young pulsars that are going 300 kilometers a second. But there are a few lines of evidence that there's kind of a second population of neutron stars that are born with lower kicks. There's these objects. If you look at the eccentricities of BE X-ray binaries, several of those are low. And then we see neutron stars that are retained in globular clusters, and they must have been born with pretty weak kicks to stay bound. So there are different models for how you can come up with this. One idea is you get a weaker kick in the neutron star if you strip off the envelope first, so that the core, only the inner core is left when it collapses. Or maybe you get weaker kicks if these are electron capture supernovae that make low mass neutron stars. But yeah, it's pretty uncertain.
Okay, well, let's thank him again for many good answers. As usual, there'll be a reception.